Good morning. So welcome to the fourth lecture of MAT-501. So last time we have seen, just a minute. Yeah. Just a minute. I'm just sharing. Yeah. Yeah. So last time we have seen functions. Actually, we started chapter number 2. So in that, we have seen, see. So first we define function. Then we have seen different types of function. So first type, there is one-one mapping. Second type, there is onto mapping. So yeah, third, that is one-to-one mapping. Then we have seen some particular mappings in that. So first equal mapping, second identity mapping, third constant mappings, then restriction and extension of mapping. So we have seen it with figure. Then we have seen definition of inverse mapping. When inverse mapping exists for given mapping. So initial mapping should be one and onto. So that is necessary condition for given mapping. Yeah. So then we have seen one theorem. Yesterday we have seen one theorem with its proof. So next, so we'll see first definition of composite mapping, and then we'll continue the remaining theorems. So first, what is the definition of composite mapping? Let's see. So composite mapping. Already this part we have seen in MAT-502. Just to revise it. So what is composite mapping? See, suppose here is a mapping from capital X to capital Y, and suppose G is another mapping and it is from suppose Y to Z. So then what is the composition mappings? So let's suppose F and G are two mappings. B, two mappings. The composite mapping of F and G, the composite mapping of F and G is denoted by this notation, is denoted by G of F. G of F. Actually, this is notation for composition of F and G. So first mapping is F and second mapping is G. Then what is the notation for composition of F and G? The G of F. See, and it's defined as the mapping see, G of F, it is mapping from X to Z. F is from X to Y, G is from Y to Z. Then G of F, that is composition of F and G, it is mapping from X to Z. So Y is common to these mappings. See, so what is the definition of this mapping? So G of F is a mapping from X to Z, and it's defined by what is G of F of X? What is the definition of this? See, so the G of F is a mapping, so you can write it in the bracket, in the square bracket you can write. So this single mapping, G of F is, so third mapping, first mapping is F, second mapping is G. So third mapping G of F, it is composition of F and G. And what is the definition of this? So it is defined by, so G in the square bracket you can write Fx. So G of Fx, and it is true for all x belongs to X. So this is the definition of composite mapping. So already we have seen it. So geometrically or by figure you can just illustrate it. So just we have seen, suppose it is X. So you can write it is X. Then suppose it is Y. And suppose it is Z. See, so it is Y, it is Z. So F is a mapping from X to Y. So this is F. F is from X to Y, and G is from Y to Z. So then what is composition of these two mappings? See, so composite mapping of F and G is from X to Z. So this is composition of G and F. And how it is defined? Let us see. Suppose, so small x is one element of capital X. Suppose it is here. So then Fx will be here. So what is the image of Fx under G? So it will be here somewhere. So G of Fx. So what is composition mapping? Composition mapping G of F match. See, X to G of Fx. So this is the definition of composition mapping. So geometrically you can observe composition mapping. So this is about composition mapping. If you are interested, you can see one example of composition mapping. So let us consider. See, example of composite mapping. So let suppose F is a mapping from R to R. See, and G is again mapping from R to R. See, F and G are two mappings, and these are defined by so fx equal to sin x and gx equal to suppose x square. Then question is that then find f of g and g of f, that is composition of f and g and g and f. So let's find. So solution. So using definition of composition mapping, so we have, see, so we have what is f of g of x. So just to have seen definition, and using that definition we'll write, see, so it will be f of gx. So what is that? What is gx? So gx is x square, so it is f of x square. I'm just writing gx, which is x square. Definition of g. And again, I'm using definition of f. What is f? Fx, it is sin x. So what is fx square? It is sin x square. So it will be sine of x square. See, similarly, what will be g of f? See, what is g of f? So g of x will be equal to, using definition of composite mapping, so it will be g of fx. So I'm just putting value of fx, that is the definition of f, which is nothing but sin x. So it will be g of fx, that is sin x. See, so that will be equal to, so what's the definition of g? So gx equal to x square, so it will be sin x sin square. So it will be sin square x. So you can observe here, what is value of f of g? So it is sin of x square, and g of x, it is sin square x. So here you can observe, see, as a note you can write, see, here we observe that, so f of g can write x is not equal to g of x, f of x, always. In bracket you can write always. See, so is there. So this is about composite mapping. So next we will see some theorems. So next, theorem 2. So first theorem already we have seen last time. So second theorem. So theorem, statement of theorem is that if f is a mapping from capital A to capital B, this is first mapping, and capital X and capital Y are subsets of B. So then, see, what is statement of theorem? then F inverse of X union Y will be equal to F inverse of X union F inverse of Y. So this is statement of this theorem. You can write this statement in words also. So image of union of two sets is union of their inverses. See, X and Y are two subsets of B. Then what is inverse of X union Y? So it will be inverse of X union inverse of Y under F. So we'll prove this theorem. Proof. So proof of this theorem. To prove this theorem, we have to prove this identity. See, so these two are sets. F inverse of X union Y set, F inverse of X union F inverse of Y set, and just yesterday we have seen definition of equality of two sets. When we say two sets are equal, if they are subsets of each other. See, so we have to prove F inverse of X union Y equal to F inverse of X union F inverse of Y. And we should prove these two sets are subsets of each other. So let us see. See, you can read it as part 1. What will prove? So part 1. In part 1, we'll prove or claim is that F inverse of, see, X union Y is a subset of, let us see, F inverse of X union F inverse of Y. So that is the first part. So to prove F inverse of X union Y is a subset of F inverse of X union F inverse of Y. So let us take one element from this and let us prove this here. See. So let's suppose I'm taking a small a. See. So then, or it will imply. So then we'll write. So A is element of F inverse of X union Y. So it will imply that F of A is element of X union Y. See, hence it will imply. See, F of A is element of X, or see, F of A is element of Y. So it will imply. See, F is element of X or F is element of 1. So it will imply A is element of F inverse of X or A is element of F inverse of Y. See, so it will imply A is element of F inverse of X union F inverse of Y. So what we proved here, that is, see, if small a is element of F inverse of X union Y, then A is element of F inverse of X union F inverse of 1. See, so that is what we have proved here. So it will imply, hence we'll write F inverse of X union Y is a subset of F inverse of X union F inverse of Y. So in part 2, or you write it as suppose equation number 1. In part 2, we'll prove part 2 or claims that, see, claim is that F inverse of X union F inverse of Y is a subset of F inverse of X union Y. So that is a claim here. See, again, in similar way, to prove this, so first let us take one element from F inverse of X union F inverse of Y, and let us put it in F inverse of X union Y. So for that, so let suppose I'm taking small b is element of F inverse of X union F inverse of Y. See, so then what it will imply? So then B is an element of F inverse of X, or B is element of F inverse of Y. Is it okay? So it will imply that, see, F of B is element of X, or F of B is element of Y. Is it okay? So that will imply F of B is element of X union Y, or it will imply B is element of F inverse of X union Y. So what it imply? That is, so we take B from this set and we prove B in F inverse of X union Y. So what it imply? That is, see, that is, if B is element of F inverse of X union F inverse of Y, then B is element of F inverse of X union Y. See, hence, what will you get? Hence, F inverse of X union F inverse of Y is subset of F inverse of X union Y. So you can write it as suppose equation number 2. So from 1 and 2, so what we get? We obtain F inverse of X union Y will be equal to F inverse of X union F inverse of Y, and which is proof of this theorem. So how we prove this? Let us see. So we have to, we have to prove that F inverse of X union Y equal to F inverse of X union F inverse of Y. So these are two sets. We use definition of equality of sets. So we prove these two sets are subsets of each other. So first we prove first set is subset of second set in first part, and in second part we prove second set is subset of first, and therefore these two sets are equal. So this is proof of this theorem. That is theorem number 2. So next we'll prove second theorem. Actually, it is third theorem here. So next theorem. Theorem 3. See, what statement? The statement is that if F is a mapping from capital A to capital B, and capital X is subset of B, and capital Y is also subset of B. It is here. Then see, what is F inverse of X intersection Y? So it will be equal to F inverse of X intersection F inverse of Y. So same as theorem, last theorem. So we'll throw this. So these two sets are equal. So we are using definition of equality of set. So for that, we will prove these two sets are subsets of each other. So part 1 will prove. See, our claim is that F inverse of X intersection Y is subset of F inverse of Y, F inverse of X intersection F inverse of Y. So we'll prove this in first part. See, for that, suppose, so let's take one element from this set and let's prove it is here. So let small a is element of F inverse of X intersection Y. See, so it will imply A is element of, sorry, so A is element of F inverse of X intersection Y. So it will imply F of A is element of X intersection Y. See, so it will imply F of A is element of X and F of A is element of Y. So it will imply A is element of F inverse of X and A is element of F inverse of Y. Or that will imply A is element of F inverse of X intersection F inverse of Y. See, so it gives that. Hence, what we get here, hence, see, so F inverse of X intersection Y is a subset of F inverse of X intersection F inverse of Y. So you can write it as equation number 1. So in similar way, what we did in last theorem, so part 2, see, so here what is our claim? Our claim is that F inverse of X intersection F inverse of Y is a subset of F inverse of X intersection Y. See, so for this, so for that, let us take one element from here and let us put it here. So let's suppose small b is element of F inverse of X intersection F inverse of Y. So it will imply, see, so B is element of F inverse of X and B is element of F inverse of Y. So it will imply F of B is element of X and F of B is element of Y. So it will imply F of B is element of X intersection Y. So it will imply B is element of F inverse of X intersection Y. So what it will imply, let's see. Hence we'll write, hence F inverse of X intersection F inverse of Y will be subset of F inverse of X intersection Y. So that is equation number 2. So from 1 and 2, what we will get? See, so from 1 and 2, we obtain F inverse of x intersection y will be equal to F inverse of x intersection F inverse of y, and this is our required equality. So this is proof of theorem 3. So next we'll prove theorem number 4. So statement of theorem 4. See, if F is a mapping from, so F is a mapping from capital A to capital B, and here I'm taking subsets of A. So in last two theorems, I have taken A and B subsets of B, that is codomain. Here I'm taking, see, x and y. X is subset of A, also y is subset of A. So I'm not taking subset of B, but I'm taking subsets of A. So this difference here. So then what is statement? Then f of x union y is equal to f of x union f of y. See, so this is statement of this theorem. If f is mapping from A to B and x and y are subsets of A, then f of x union y equal to f of x union f of y. So we'll prove this theorem. So which is similar. So what we have did in last theorem, same thing we are doing here. Let us see. So proof. So again, to prove this equality, see, equality of two sets. Two sets are equal if they are subsets of each other. I'm using same logic again and again. So part 1, what is my claim? So here our claim is that, so we'll throw f of x union y is a subset of f of x union f of y. See, so for that, so let us take, suppose, see, suppose B is element of f of x union y. So we are taking one element from here and we'll prove this element is here. See, so B is element of f of x union y. So what it imply? So then you'll write small b as f of a. But what is A? A is element of x union y. So here for some you'll write, for some small a belongs to x union y. So A is element of x union y. So it will imply A is element of x union y implies that A is element of x or A is element of y. So it will imply, see, f of A is element of f of x or f of A is element of f of y. See how we are writing this. If A is element of x implies that f of A is element of fx, and if A is element of y implies that f of A is element of f of y, because it is mapping. So using that, what we'll write? So it implies f of A is element of f of x union f of y. But what is f of A? F of A is nothing but B. So that will imply B is element of f of x union f of y. So it will imply, let us see. So we take B from f of x union y and we put it in f of x union f of y. So it will imply, see, f of x union y is a subset of f of x union f of y. So you can write this equation as, suppose, equation number 1. So in second part, that is part 2, See, so what is our claim? Our claim is that the reverse inequality, that is f of x union f of y is a subset of f of x union y. So that is a claim. See, so I will take one element from here and I will put it is here. So for that, see, so let's suppose small c is element of f of x union f of y. C is the element of f of x union f of y. So it will imply small c is the element of f of x, or small c is element of f of y. So what it imply? So what is the meaning of this? That is, you'll write, it will imply small c is image of c. C is an image of some point in x, is image of some point in x. I will write, I'm writing this. So I will write in color. See, I'm writing c belongs to fx as c is an image of some point in x. Its meaning is that, and let us see what is the meaning of c belongs to f of y, or c is image of some point in y. Let us see. So I'm writing meaning of c belongs to f of y as c is an image of some point in y. See. So what it implies that c is the image of some point in x, or c is the image of some point in y. So it will imply c is image of some point in x union y, because it is image of some points in x as well as some points in y. So that will imply it is image of some points in x union y. So it will implies that, what is the meaning of this statement? That is, c belongs to c so that will imply c belongs to f of x union y. It's okay. So that is what we have to prove. So we take c from fx union fy and we prove it is in f of x union y. So hence what we get, hence see, f of x union f of y is subset of f of x union f of y. So you write it as was equation number 2. So from 1 and 2, what we get? C. So from 1 and 2, we obtain f of x union y will be same as f of x union f of y, and which is proof of this theorem. See. So next theorem we'll see in next lecture. So we'll stop here. See.